Have you ever really stopped to wonder how a machine actually learns? We hear all the time about AI understanding language, but what's really going on under the hood? Well, today, we're going to pull back the curtain on a super important but often overlooked piece of that puzzle. Let's dive in.
Okay, think about your email for a second. Every single day, there's an algorithm in there, sorting through everything, trying to figure out what's important and what's just junk. But how? It's not like it's sitting there reading about some once-in-a-lifetime offer and rolling its digital eyes, right? The truth is actually way more fascinating.
And here it is. This is the absolute core of the whole thing. A machine learning model, I don't care how powerful or sophisticated it is, has one fundamental limitation. It literally cannot read. If you give it an email or a news article, it just sees a meaningless jumble of characters. It has zero built-in understanding of language.
That's the secret sauce. At the end of the day, algorithms are just math. They run on equations, and to do that, they need numbers. They don't get words, they get vectors, long lists of numbers that represent the world. In this whole process, this art of turning our messy, complicated world into clean numbers that a machine can understand, that's called feature engineering.
So how do we even start this translation process? Well, it all begins with two really basic concepts. Let's break down exactly what we mean when we say features.
It's a really simple but powerful idea. Features are just the inputs you give the model, all the data it gets to look at. You can think of them as the questions you're asking it. And the labels? Well, those are the correct outputs. They're the answers. When you're training a model, its entire job is just to figure out the connection between the questions and the answers.
Let's make this super concrete. Say we're predicting house prices. The features would be things you can measure, right? The square footage, how many bedrooms it has, the zip code. And the label? That's the final sale price. The model crunches thousands of these examples to learn how those features usually lead to that price.
Okay, so that makes sense for things that are already numbers, like square feet. But what about text? How on earth do you turn a sentence into a list of numbers that a machine can actually work with? This, my friends, is where the real art and science of this whole thing begins.
This quote from Machine Learning Mastery it hits the nail on the head. This one single problem is the entire reason the field of natural language processing, or NLP, even exists. We literally had to invent ways to give machines the senses they need to perceive our language.
And the solution we came up with is something called a feature vector. It's just a fancy term for a list of numbers that acts like a numerical fingerprint for an object, whether that object is an email, a picture, or a sound. The whole game is just about creating the most descriptive, most meaningful feature vector you possibly can.
Now, the methods for creating these vectors from text have changed a lot. It's a story that takes us from something as simple as just counting words, all the way to understanding the deep, subtle meaning behind them. Let's actually walk through that evolution.
We're going to look at this journey in three major leaps. First, we have the most basic approach you can imagine, literally just counting words. Then, we take a huge step forward to actually capture the meaning of individual words. And finally, we get to the current state of the art, understanding that a word's meaning can change completely depending on its context.
So, the first and most obvious idea, right? Just count how many times each word shows up. But you hit a massive wall almost immediately. Super common words like the, is, and a are always going to have the highest counts, but they tell you absolutely nothing about what the text is actually about. They're just grammatical noise.
And this problem leads us to our first really clever solution, TF-IDF. You can think of it like a statistical balancing act. It looks at how often a word appears in one single document, but it also looks at how often it appears across all the other documents. So a word like data might be everywhere, and its importance gets pushed down. But a rare word, something like hallucination in a paper about AI, whoa, that's a huge signal, and its score gets a massive boost. But even TF-IDF has a big blind spot. It has no concept of semantics, of what words actually mean. To this algorithm, the words good and excellent are just two totally different strings of letters. It has no clue they mean almost the exact same thing. To solve that, we have to go beyond just keywords and start capturing meaning itself. And this is where things get really cool. This brings us to word embeddings. From models like Glove, these things are trained on billions of words to learn the relationships between them. They map every word to a point in this high-dimensional space, where the distance between points represents meaning. This is how an algorithm can literally learn that king is to queen as man is to woman. It's doing analogies with math.
Okay, so now we can represent words with their actual meaning. Great. A common way to get a vector for a whole sentence is to just average the vectors of all its words. But, oh boy, this creates a new, massive problem. The sentences, the dog bit the man and the man bit the dog, use the exact same words. So their average vector? It's identical. The model has absolutely no way of knowing who bit whom. All the context is gone.
And that problem brings us right up to the modern day, to the era of transformers. That's the architecture behind models like BERT and GPT. They use a mechanism called self-attention to read the entire sentence all at once. This lets them understand that the word bank means one thing in riverbank and something completely different in financial bank, because it's paying attention to all the surrounding words. This was the leap that finally unlocked truly context-aware AI.
So, we've seen how these techniques have gotten more and more powerful, but also way more complex. And that leads to a new question. What if we could automate this whole messy process? What if an AI could just figure out the best features all by itself?
See, for the longest time, feature engineering has been seen as this expert-level task. A mix of deep knowledge about the subject, a lot of intuition, and tons of trial and error. It's a craft, but like a lot of crafts, it is now totally ripe for automation.
This is where you get to the absolute cutting edge, with research like LLMFE. And the core idea here is frankly incredible. You use one AI, a big large language model, as a kind of creative engine to dream up and build the best possible features for a different, more specialized AI model to use.
And the way it works is basically like this little evolutionary loop. The big language model generates a hypothesis, it proposes a new feature. Then that feature gets built and tested to see if it actually helps the other model make better predictions. The results, what worked, what didn't, are fed back to the LLM. It learns, and it makes a smarter guess the next time. It is AI-driven evolution, and it can discover things that might take a human expert forever to find.
So think about where we started. We had this simple problem. Machines can't read. The solution was to translate our world into numbers for them, a translation that went from basic counting to this deep contextual understanding. And now AI is learning to perform that translation all by itself. We're not just teaching it to see the world as we do. We're giving it the ability to invent totally new ways of perceiving reality. And that leaves us with a pretty fascinating question to think about.